Hi everyone, today we're going to talk about quotient and precipitation. Quotient is the ion product. When two solutions are mixed together, the reaction quotient Q, or ion product, is used to predict if precipitation will occur or not. Now Q is written in the same way as KSP, but not based on equilibrium concentrations, rather based on initial concentrations. If the quotient calculated is equal to KSP, that means the solution is saturated. If the quotient is greater than KSP, that means a precipitate will form, meaning forming a supersaturated solution. If the quotient is less than KSP, all the ions remain in solution and no precipitation will form. The solution is still unsaturated. Now, you might have seen a demo like this in your classroom from your teacher, that a supersaturated sodium acetate solution can be prepared by dissolving solute in water at a higher temperature. Now, then the solution will be cooled down. At this time, the solution is unstable, in which quotient is greater than K. However, when you put a small seed crystal into the solution of sodium acetate, the whole crystal will then precipitate out and forming very interesting structure. And you might have seen this before, and students often find this very amazing demo. Let's try practice problem number 1. If we have 20 ml or 0.0035 molar silver nitrate mixed with 40 ml or 0.002 molar NaCl, will a precipitate form or not? First, we need to know the KSP of silver chloride, 1.6 times 10 to the minus 10, that we look up from a table in your textbook. Now, let's calculate the initial concentration of silver ion, the little zero, meaning initial at time 0. So we have 0.0035 molar times 20 ml over a total mixture of 60 ml. And we have 1.2 times 10 to the minus 3 molar. For the chloride ion initial concentration, we calculate it in a similar fashion, 0.0020 molar times 40 ml over 60 ml. And we have 1.3 times 10 to the minus 3 molar. Now we set up the quotient, which is equal to silver ion initial concentration times chloride ion initial concentration, which is equal to 1.6 times 10 to the negative 6. Now, if we compare that with the KSP, the quotient is greater than KSP. That means the precipitate of silver chloride will form when we pour the mixture together. Practice problem number 2. Now we have calcium nitrate, 280 milliliter, 1 times 10 to the minus 2 molar, added to 20 milliliter of 5 times 10 to the minus 1 molar sodium fluoride. Let's calculate the concentration of calcium and fluoride ion at equilibrium. KSP is 4.0 times 10 to the minus 11. First, we calculate the initial concentration of calcium ion, which is 1 times 10 to the minus 2 molar times 280 milliliter in a total mixture volume of 300 ml. This is adding 280 to 20 to get 300. Now it is equal to 9.33 times 10 to the minus 3 molar. In a similar fashion, we calculate the initial concentration of fluoride ion, and we find it to be 3.33 times 10 to the negative 2 molar. Now you set up the quotient, which is initial concentration of calcium ion times initial concentration of fluoride ion raised to the power of 2 because of the coefficient of 2 in the dissociation stoichiometry. So when we multiply the terms together, we have 1.03 times 10 to the negative 5. The quotient is greater than the KSP. That means precipitation will form. Now we need to use this number and carry on further to calculate concentration of the ions at equilibrium. So to continue, let's first find out the initial moles of calcium ion, which is 2.80 millimoles. I like to use millimole to calculate so that I don't have to convert it into liter. I can worry about that a bit later. Especially when I don't have a calculator, the millimole becomes very handy. Now the fluoride ion is 10 millimole. Now I set up the ice table, and I start out with 2.80 millimole of calcium ion, 10.0 millimole of fluoride ion. Now I would then, this is a limiting reactant, so I use up all my calcium ion. I would use up twice amount for the fluoride ion. So I now have 4.4 mole of the fluoride ion remaining, and this is in a mixture of 300 milliliter, and I get 0.015 molar. Notice how I divide millimole by milliliter without having to convert them into mole and liter, and I still get up the molarity. This is much easier to do. Now, continuing, this calcium fluoride solid that precipitated out will be dissolved to reach equilibrium according to the following equation. So initially, I have 0.015 molar of fluoride ion as an excess from the previous stoichiometry. Now, I add X to the calcium ion and 2X to the fluoride ion. I end up with X for the calcium ion and 0.015 plus 2X for the fluoride ion at equilibrium. Now I write the KSP, set up the expression, calcium ion times fluoride ion raised to the power 2. And then I substitute the numbers in there. Now, because this 2X is much smaller than the 0.015 due to the small KSP, therefore I can drop the 2X from my expression when I calculate and solve for X, which is then 1.8 times 10 to the minus 7 molar for the calcium ion concentration. And the fluoride is still 0.015 molar. So it will be good for you to find some problem to practice along this concept. Selective precipitation. If we have a mixture of two different kinds of ions, or more than two, in an aqueous solution, we can separate them out one at a time by adding a reagent that will form a precipitate with the ion that has a lower solubility. Let's say I have 250 milliliter of a solution mixture containing hydroxide and sulfate ion, each one present in 0.1 molar. Which ion will precipitate first? When I add the 0.002 molar of calcium nitrate to it, and what's the minimum volume of calcium nitrate that's required to form the precipitation in A? So here's a picture. I have my initial beaker of 250 milliliter containing 0.1 molar of sulfate and hydroxide. I'm adding the calcium nitrate. So let's write the equation for the dissolving of calcium hydroxide and write the KSP expression. Now, using the KSP value of calcium hydroxide, we want to calculate the concentration of calcium ion required to make precipitation, and we use 0.1 molar of the hydroxide ion already present in the beaker. So the calcium ion concentration is calculated as 1.3 times 10 to the minus 4 molar required to make calcium hydroxide precipitate. Similarly, we do the same solving for the calcium ion concentration required to make the precipitate of calcium sulfate in that beaker. Now, this comes out to be 6.1 times 10 to the minus 4 molar. Clearly, the calcium ion required to make the precipitate of calcium hydroxide is smaller than that required to make calcium sulfate precipitate. Therefore, the calcium hydroxide will form precipitate first, and you see that in the beaker. And this is a recap of what I just said earlier. Now let's calculate the volume of calcium nitrate needed to form the precipitation. Now remember, in the beaker we have 250 milliliter, which is 0.250 liter of the mixture solution, and we require 1.3 times 10 to the minus 4 molar of calcium ion per my earlier calculation. So now I'm adding 0.0020 molar of the calcium nitrate. What's the volume required? It's calculated to be 16 milliliter. To sum up what we have learned today, we have learned using ion product quotient Q and compare that with K to predict whether precipitation will occur or not when two solutions are poured together. we learned about the precipitation of a supersaturated solution. For example, we talk about sodium acetate. And we learned how to do quantitative calculations involving quotient and ion concentration at equilibrium. Finally, we calculated, based on selective precipitation, the amount of reagent to be added to form a precipitate and which ion from the mixture will precipitate first. I hope that you have found the video helpful to you. If you like it, please give us a like. And I look forward to seeing you again in the next part of KSP.